And good evening and welcome back to our page, Astronomy by the Bay. It's Chris Kerwin back with you again on this Sunday night, another cloudy Sunday night here at St. John. This is our seventh episode so far, and we've only had 2 clear skies out of 7. So we're really trying hard to try to bring things to you, but we're going to keep at it as long as we can and just offer what we can for you this evening and future nights if the sky doesn't cooperate, which seems to be the way here in Maritime Canada. Right now, tonight, I've got Paul Owen on with me. Paul's in Hampton tonight, and Mike Powell is on with me from St. John. Say hi, guys.
Hi, guys.
Hi, guys.
Perfect. So I've got the YouTube live stream sitting here too, so we're ready to answer questions as they come in or any comments that come in. So we're going to start off with a talk here from Mike. Mike's going to give us a talk about how to listen to meteors during a meteor shower like we had the other day with the quadrantids. Of course, we were clouded out here until early morning, and apparently there was a few people here in town that did get a chance to see some of them there early morning. But we're going to try listening to meteors on a cloudy night. So I'm going to let Mike take this away. If there is anybody on here that wants to comment and let us know about our volume level, if it all seems to be coming through okay, that would be great. And here comes Mike.
Whenever you're ready. Yeah.
I think we're ready to go.
Well, it's kind of funny how often it is, Chris, we go down to the beach and we're all set up and people come down going, is there something going on tonight? And we're going, not really. Are you here to see the meteor shower? And it's like, not really. But they come down just to strictly see the meteor shower on the day that CBC or the news or whatever tells them to be there. And, number one, they don't realize that a meteor shower runs over a certain length of time, not just one night. That's the peak night that the meteors come through. And like I said, on a lot of nights, it's a cloudy night. You don't get a chance to see anything anyway. Or if you're in the city, you got the city lights that washes out a lot of it. But I came across an article a few years back, and it was called Listening to Meteors. And it was kind of cool. It's a real simple thing to do. And by the way, if it's out in space, it's called a meteoroid. If it's coming through the atmosphere, it's a meteor. And if it hits the Earth, it's a meteorite. So it's all about picking up when these meteors are coming through the atmosphere. So it's pretty simple. You know, when you go out, you can do a few things. I guess my page looks like it's a little bit stretched, but you can go out and watch them. You can take your camera with you. You can try to photograph them. If you're one of the group that has an all-sky cam, you can capture them that way. And that's one thing I got to get set up next to my observatory is the all-sky cam. But you can actually listen to them when they're entering the atmosphere. They come through and they will break a radio signal. Or if you choose, to sit in the house and not go outside and try to look or try to listen, you can actually go onto a website called spaceweatherradio.com, and it's down in Texas, and you can watch their screen, and you can see when the meteors are coming through, and you can actually listen to the meteors coming through the atmosphere, which is pretty cool, and you can do it live. You can go right to their site, just log in, spaceweatherradio.com. You click the button that says listen, and sit back, and you can hear the meteors coming through the atmosphere. Or, if you want to do it on your own, really all you need is a simple AM/FM radio, a transistor. You can buy them pretty much anywhere. Most people have one. You have mostly AM/FM in your car or truck. You can go down to Value Village and pick up one for 99 cents or $2 or whatever. Throw a couple of batteries in, and you're going, well, how does that work on an AM or FM radio? Well, when you're listening, what you want to do is first off, is the meteors will enter through the atmosphere, and that tail will ionize the air. When it does that, the radio signal will bounce off the ionized air, and it can be picked up as a ping on the radio station that you're listening to. And all you got to do is tune in and listen. Now, it's pretty simple to tune in. What you want to look for is an FM radio station, and let's choose FM because it's probably the easiest. It's the one that most people listen to. There's not a whole lot on AM anymore. So you take your FM radio and you tune it into a frequency or a radio station that you know is there, but you cannot hear it. It's too far away. Something about 1,000 kilometers away or 500 kilometers away is perfect, because you won't hear the signal when you put your radio on that station. Now, as the meteor passes between you and that radio station, it ionizes the air with the tail, and that signal will reflect down back to your antenna. And if you're listening, you will pick up something called a ping. So just you can go on a website. CBC Radio has all their stations listed. You'll find a radio map like the one you see here on the screen, and that tells you how broad their signals are. So you want to pick up something, say if you're in St. John, New Brunswick, you want to look for a Montreal station or a Quebec station and tune into that station to a point where you can't hear it, but you know you're on the right station. When the meteor passes through, you will hear a ping. And if I can get it to change channels here. Oh, it's not picking up the sounds anymore. If I get something muted, maybe. Now, there's our first glitch. When I was running the program here, I hear a ping, and it's literally just a ping. You hear a whole bunch of static, then you hear a ping, and then static again, and that's the meteor coming through. You can go a step further, which I have for my observatory, of course, me being me, and you can set up your own little listening station for it. I went on eBay and I bought a TV FM radio antenna. It cost me a total of $22 shipped to my house from Amazon. They're relatively cheap because nobody's buying TV FM antennas anymore and they want to get rid of them. So, you know, anywhere between 15 and 25 bucks, you can buy this antenna right here and you can mount it up. You have to get a TV or an FM PCI tuner card, which are getting more rare to buy. Nobody wants to buy PC parts anymore. But there's something called an SDR dongle, which stands for Software Defined Radio. You can buy any SDR radio dongle on eBay, starting at 10 bucks, free shipping, all the way up to 100 bucks, depending on how much you want to spread or spend. And they will cover a frequency range everywhere from 10 megahertz or kilohertz, sorry, 10 kilohertz all the way up to 2 gigahertz. So you can tune into any TV, radio, ham radio station you want. You can pick it up and listen to them. And it works the same way with this system. That plugs into your PC. And then you download some Spectrum Analyzer software, which is free again if you type in Spectrum Analyzer software. And you can actually watch the waterfall come down. When a meteor goes across and it breaks the signal and you hear a ping, it will put a line on the waterfall screen down here. You'll see a line stretch out across. So you're actually watching the meteor coming through at the same time you're listening to it.
Nice.
Now, it's a pretty simple setup. Radio is like line of sight. So if you're far enough away, the curve of the Earth will break the radio signal, right? So you want something that's going to enough distance between you and the radio station you're listening to break that signal.
Wait now, Earth curvature?
Yeah.
Okay.
The curve of the Earth, the signal won't pass through the Earth.
Okay,
It's curved.
Earth. Okay.
It could be the pizza or plate shaped curve.
Yeah. Okay.
Whatever you like.
Okay.
When the meteor comes through there, my little buddy in the corner, the signal will bounce off him and come down to the receiving antenna. Come on down to the receiving antenna. It's glitching up on me. Then I go down into your receiver, TV tuner card, or SDR dongle, whichever one you have. That's plugged into your USB port into your computer. And from that computer, you bring up the radio or Spectrum Analyzer software, and you hear a ping.
There's your ping.
Did you hear the ping?
Yeah.
Let me go back and try that again. You can actually hear the ping this time. So there comes the meteor through the atmosphere. The signal will come down through the antenna, through the radio receiver, into the laptop, onto your Spectrum software, and if you're lucky, you hear the ping.
I heard a scratch.
That same ping can be picked up on your FM radio when you're sitting at the beach, having a nice hot coffee, watching for meteorites, or tuning in your radio and listening. It's a simple, simple thing to do. All you got to do is find that station that's too far away from you for you to normally pick up, and between you and that station. So that's listening to meteorites. It's a very, very simple thing to do, fun. And if you're sitting out looking anyway, you might as well take an FM radio with you. And if nothing else, you can listen to static.
Nice.
That's pretty much it. It's a simple thing to do, but it's kind of fun.
So,
Thanks,
Mike, can I ask a question?
Sure.
So if a cloud's over while you're out there, so long as it's not raining, you may not be able to see things going in the sky, but you can still hear the ping because it's being picked up from radio. So
Absolutely.
It doesn't care if
That's
it's cloudy or not.
Yeah, that's the advantage to any type of radio astronomy is it doesn't matter what the weather's like. You can pick up a radio signal. The visual spectrum is very, very small in the width of what we, can pick up in the electromagnetic band. The electromagnetic band is just a radio signal. Jupiter itself puts out 2 trillion watts of power, and you can actually set up a system to listen to that too. But this is all about picking up, meteors coming through tonight. That was a whole nother program that I have for setting up the itty bitty radio telescope and listening to meteors and listen to the sun. But for this one, like I said, you can go down to Value Village, spend 99 cents, buy a transistor radio, put a couple of batteries in, tune into an FM frequency that you know is there, but you can't hear from here.
Right.
And set it beside you. And while you're watching, you just wait. Or if it's cloudy and you want to sit at home, you can turn it on and just wait. Through the static, you will hear the pings. It's quite impressive. The first time you hear a ping, you get a smile on your face. I'll tell you that. To say, wow, it does work.
Mike, Dave McCashin was asking, do you hear more than what you'd see if you were watching at the same time? I guess the question would be yes.
Absolutely. But you got to remember, that meteor is going to be passing between you and the radio station, right? You might see one that's way up there that, could be passing over Vancouver for all I know. That one you may not hear, but if it so happens to break the path between you and the radio station you're listening to, that's when you hear them. Like I said, it's a fun thing to do. If you're going to sit there, you might as well take a radio and listen to them as well. You probably pick up more on the radio than you will visually.
All right.
Thanks, Mike.
No worries.
Lots there to absorb for sure. I wonder if you can are you going to be able to put that up on the St. John Astronomy Club maybe website?
I absolutely can send it to that Jim there, and when we get it up there, yeah.
Great. Okay. So yeah, I wanted to let everybody know too that we're all members of the St. John Astronomy Club here in St. John, New Brunswick, and also the Royal Astronomical Society of Canada, the New Brunswick chapter, and across Canada, there's a little over 5,000 members. But what we also do is we have a really nice website. The St. John Astronomy Club has a huge website. Jim Stewart, our local guy, set it up for us, and he did a fantastic job. There's tons of information in there, and most of the presentations that we'll present here will be available up there on the website for download if you like. So you can always go to our St. John Astronomy Club site. It's just sjastronomy.ca. And go in and take a look. You'll see that there's a pile of information there for you to enjoy for sure. We'll have to get you on again, Mike, about the itty bitty radio telescope sometime.
Yeah. I'll stop sharing.
Okay.
I'll stop sharing the page here, and then people can see us. How's that?
Great. Here we are.
Yeah.
We're back. Yeah, that was perfect. Thanks very much. So any more questions? I'm just watching for questions. Dave McCashin says, have you listened for them? If so, how many per hour is the most that you've heard? Are you there, Mike?
Oh boy. Yeah, I'm here.
Okay.
How often have I done it? When I was out at the observatory last summer, I probably picked up where I was sitting back on the roof, open and look up. I might have seen 150 pings on a night that was a peak, and I forget which one it was actually, which meteor shower it actually was, but it was a busy radio night for sure.
Okay.
Ham radio operators, they know all about it. It's called something called meteor scatter, and they actually use it. So anybody that's got a ham radio already knows what I'm talking about. But for any amateur, person that knows nothing about radio astronomy, just like I said, a normal FM radio will do. You just tune it into a frequency of a station that you know is there, but you can't hear.
Right.
And eventually, through that static, you'll start hearing the pings.
Nice. That's great. That's a nice, easy way, though, is with the FM radio for sure. That's a great idea. We should have that set up at the beach.
Yeah, we should.
Observing, and, yeah. If we can't see them, at least we'll hear them.
I have one right here.
I'm not sure if your video's choppy
Yeah.
to anybody out there or not, but it was coming in just a bit choppy to me. But seems to be, it might be okay. Anyway,
You just have to go slow.
we talk really slow, and so everyone can hear. Who's up next? Hey, Paul's up
Sounds
next.
like somebody I know.
Oh, come
Oh,
on now.
bother.
Oh, bother. Yeah, oh, bother. Hey, look at me. I'm just sitting here having a cup of coffee. Great.
And all of us are.
Yeah, this is perfect.
Happy
Well,
coffee night, everybody.
I get it.
Coffee night.
I get all the smart guys here, so all I have to do is host it. Well, Paul's going to give us our next talk, and Paul is going to give us a talk on astrophotography, what it's all about. And he's going to chew up some time here for sure. So if you have questions, maybe Paul, maybe as we work through it, if there's any questions, I can let you know.
All right.
Okay.
That's great. All right. I'm just going to see if I can't do this correctly.
Paul is our resident astrophotographer. He's done a lot of photography. If you go to his Facebook page and other sites, actually, Paul has put up a lot of material. So he's our resident expert for sure, and he's going to teach us a little bit about how to do it.
Okay. Just let me tell me if you see that on the screen.
I see astrophotography. What does it mean?
Perfect. Thank you so much. Okay. So I'm going to preface this a little bit first, or preface, however you want to say it. So this is not for someone who's already a budding astrophotographer, and I see a couple of them online already. And but what this is going to explain is just a little bit of the differences between regular photography and what you do to take a photograph versus astrophotography, and some of the things that you have to do to take a photograph. And it's going to cover it's just going to touch base a little bit on planetary photography, as well as some deep sky and wide angle and a few things like that, and just what it takes to actually do those things. So it's not going to be a deep hard course. It's just basically just some very, very light, simple things that we have to do to make the difference. So I'll preface it with that. All right, so here we go. So astrophotography, what does it mean? Well, some call it the dark art. So the reason being, of course, is anything that you do when you're doing astrophotography, especially the deep sky stuff, it's pretty dark out there and you're there for long periods of time. So just like Darth sitting here with his telescope, looking back probably at the Earth or looking at somebody, he's not taking pictures, but he's certainly in the dark, and his eyes are dark adapted, I think. So astrophotography is a combination of two great hobbies or professions. And I'll start off with photography at first. And so photography, when I looked it up, this is what the meaning came up as, it was the art of capturing beauty of life, the act of appreciating the moment captured through a camera in a form of photographic images or recorded video. And so there was a picture that when I was down in Costa Rica, that's where that is, and that was a sunset. And so that picture was just so much fun to take. Plunked my camera in the sand with all the little crabs at my feet, and just pushed the button and click, and I got that nice picture. It was wonderful.
Nice.
So that's what photography is. Astronomy, on the other hand, is the scientific study of celestial objects such as stars, planets, comets, and galaxies, and phenomena that originate outside the Earth's atmosphere. So when you put the two together, of course, photography and astronomy, thus we get astrophotography. So photography and everyday photography, like once you've basically gone out, you've selected what it is that you want to take a picture of, you got the lighting right if you're doing, pictures of people, or if you're outside and, taking a nice landscape shot or a picture of a bird, you kind of set your camera up pretty quick, and then you just push the shutter and, in a fraction of a second, you've got your image. So, and then all of a sudden you can just close the camera and then go have a nice meal and go home. It's wonderful. With astrophotography, it's a little different story. And with certain types of astrophotography, just to prepare to take the image can take up to a couple of hours easily. By the time you drag your stuff out, set it all up, get your computer up and running, make sure all of your components are correct and working correctly. Then you're just getting started. Now you've already burned up a couple of hours, not to mention the drive time to get there because you want to go to a nice dark sky. So then, so once you've got that done, it's just starting to get dark. And as you can see in the background in this particular photograph, this was at Fundy National Park. There's still, we're still at twilight, still at dusk rather. So you can see the stars are just starting to pop out into the sky. So we have to wait for Polaris because we're being in the northern hemisphere so that we can polar align our telescopes in order to be able to get things so that we can get nice long pictures. So then comes the acquisition. So after all those couple of hours of getting things set up, and then another, say, 45 minutes so that you can get Polaris, do your polar alignment, that just takes a matter of a few minutes. Then you got to calibrate your camera because there's another camera on top of your telescope that you have to calibrate so that it follows the motion of the sky. And then basically that's when you can start turning on your computer or not pressing the button on your computer to start acquiring data. And so that's when you're gathering anywhere from 30 to 100 images, and they can be anywhere from 3 to 10 minutes long each. So your session could be anywhere from 1.5 to 16 hours of capture time. Once that's done, then you go into pre-processing. So before you even tear it all down, then you got to take your dark frames, which you're basically putting a cover on your telescope, taking pictures exactly the same length that your light images, the ones that the pictures you just took. So you got to do those, and you probably want to do anywhere from say 25 to 50 of those. Then you're going to do your bias frames and then some flat frames. And so these are all just calibration frames that you need to do so it takes care of the picture so that when you start to actually image it, it's not full of vignetting and dust bunnies and all kinds of other things that you would find in an optical train. And then once all that's done, then you go into a stacking procedure, and then you stack it all. So that's what you call pre-processing. Then you can start tearing your rig down and start heading back to your house, because when you get home, then you got probably another few hours of processing. This is Emil's favorite part. Anyway, another few hours of processing, which means getting that particular image into your computer. And then when you put it there and you put that image in, all you see is this piece of black. You're thinking to yourself, I spent all night doing this. I went through this whole procedure doing all these things, and all I have was just this black image. Well, no, you don't. It's in there, but now you have to stretch it to pull it out. So as you start stretching that image, you're starting to get into that data that you were actually looking for. After that's done, then you have to do a calibration for color, and then some background neutralization and some noise reduction. And if you want to do some mask for shrinking stars, these are all the things that you would do in processing, and then a whole bunch of other things, of course, but that's just sort of a skinny version of what you'd have to do. So after all of that, you would probably ask yourself, why would you want to photograph the night sky? Are you out of your mind? Mm-hmm. Well, you know what?
Yeah, Mike and I agree.
Why we do it? Because
Mike
we
and I
love
agree.
the night sky. That's why we do it. And we're crazy.
That's true.
You got to have a little element of crazy when you're doing this stuff.
Yeah, I don't know.
Anyway.
A little more than a little.
So basically, we love the night sky, and astrophotography is really, truly a way to enhance your astronomical viewing sessions. Because what you see with your eye and what you can capture with a camera are two totally different things. And once you sort of get into that astrophotography side and take your first image, and all of a sudden you're looking at this beautiful thing that you've went through all that effort and captured, and it went well, you're hooked. You really are. So, for example, if you were looking at the Andromeda Galaxy, and excuse the little squares there, that's just something happening from the process of my computer going online. Stars aren't, they're round. But in any event, when you're looking through a telescope, when you're looking at Andromeda, this is probably what you're going to see. This is a good simulation of what you're going to see when you're looking at Andromeda. And so you're getting that nice bright star in the middle. You can see some faint dust lanes. You can certainly see lots of stars. And it's really a beautiful thing to see through a telescope, just realizing that, this is, I think, 1.5 or 2.5 million light years away. And all of a sudden, that long ago, that light is striking your retina. You're actually seeing that for yourself. So you're connecting with the universe and everything that's around. That's amazing to see. But to see it photographically, then you can see what's truly around there. And then it's like, oh my gosh, look at that now. So I can see the dust lanes. I can see the little new star formations. I can see a couple of other galaxies that are there. Right up here is a galaxy. Right down here is another galaxy. I can see all kinds of nice different colors. My stars have color. It's just an absolutely wonderful image, which you can't see with your eye. So you may say to yourself, okay, wow, that's amazing. Why is there such a difference? Well, the difference being simply that our eye has limitations. So basically, everything that appears in shades of gray and even larger through amateur telescopes. And there are exceptions, of course, like the planets and some of the brighter nebulas, you might see some green hues and so on. Or if you're looking at something like the veil with the proper filter, you can actually see those teal wisps that you would see in that. But other than that, that's pretty much what you're going to see through a telescope. Reason being is that our eye looks at it. It's a very, very inefficient camera lens, if you will, when it comes to looking in the dark, because we have a couple of different ways that light is processed, and it uses the cones and the rods in our eyes. And the cones, of course, are the little color receptors that you see. If I get my mouse to work, there we go. So there's the greens, the reds, and the blues, but they are so inefficient, it's very, very hard to ignite those. And so most of our vision comes from the rods, which are giving us that luminance, and that's basically what we're seeing. So when we're trying to dark adapt our eye, what we're trying to do is have our pupil open up as large as it can, because that's what happens as it gets dark, as the pupil will start to dilate, and as it gets bigger, it allows more light to get in. So, but the trouble is as that light goes through our eye, it goes down the optical nerve into the brain, and it processes it immediately. So that's why we can't really see any more than what I was showing you earlier. So what the world of invention has come up with, of course, is the camera sensors. And the advantage there is camera sensors are eyes that actually accumulate light. So we can see everything instant to instant, where a camera can actually basically store photons. It can take this 3-minute exposure and then take another one. Let's stack that light over top of that one. Let's take another one. And it can gather all of that light and basically, keep stacking it like rain in a bucket. And also it's more sensitive to the red bandwidth of light, which is what we need to have to be able to see those nice emission nebulas, those red hydrogen alpha regions. So that's the reason why we can do so much better with a camera, and why Hubble telescope pictures look so much more beautiful than what we look at through a telescope is the limitations of our eye. Another thing I want to show you here is Sue French is one of the ladies that does a lot of sketching in one of the magazines. She does fantastic work. Actually, Emil, our fellow in Moncton, some of his sketches are amazing as well. Him and Ted Dunphy up in Fredericton. So what she was doing here, and I found this interesting. I got this on one of her sketches, and she was basically tracing M42. So what we're looking at here is the Orion Nebula, as she saw it through a 4-inch refractor. And so that's not a really big telescope. That's basically the diameter of the lens. And based on what I'm seeing here, I'm assuming it was probably about a 700 to a 900 millimeter telescope, based on the magnification. And think about this for a second. This is what she saw. And in order to sketch this, she had to be looking at this for quite some time. So her eyes are dark adapted. She's drawing this the best she can. And this is what she can see after all of that length. And that's basically what you would see through a telescope at M42, maybe just a little more than that, depending on the type of scope you have and how dark your skies are. Now, I want to show you the same thing that she was drawing and took all that time to, but I want to show it to you, a picture of it that was taken actually through a smaller telescope. And there it is. So there's the Orion Nebula M42. So what she was seeing through her telescope was, if you see this little part here, let's just pretend this is a head and these are two wings right here. So what she was seeing are these areas right here. And through a telescope, you can probably see that, depending on, again, on the sky and the type of scope you have. You can see that as a nice grayish, greenish kind of a hue. And I'll go back to that so you can see what she saw, which is right here. So that's what she was seeing when she was looking at the through her telescope. That would have been the trapezium there. So the four little stars that are in the center of that. So you can see the difference between what the human eye can see and how a camera can collect the light and show you something totally different. Now, mind you, my core is all blown out, but that's where those four little stars would have been in the thing that she was looking at. So in order to get a photograph like this, this is what I used. So it was just basically a refractor, which is, type of telescope that you would think of when you think of Galileo, who did not invent the telescope, by the way. But in any event, that's a refractor. And then I used a camera, which is just a DSLR, which a lot of us have. Now they're using mirrorless, of course. And this particular camera was modified. So all that simply means is there's a little filter in front of the sensor that was removed, which is an IR cut filter. And what that does, that allows a lot more of that red light to be picked up. I think it's somewhere in the order of 80% more of that emission level you can get when you actually modify your camera. But keep in mind, when you do that, it's not really good for daytime photography after that. Anyway, so that was the camera, and that was through the telescope here. And there was that particular target is very, very bright in the sky. So that was 25 240-second exposure, so a little under 2 hours. And the ISO setting on that was 1600. But that's basically what I used to get that picture of M42, the Orion Nebula. I'm not looking at the screen, guys, so if there are questions that are coming up, please let me know.
We're watching for them, Paul. All good so far. Yep.
Okay, good.
Apparently, we're nutty astronomers.
So next up is the telescope. So telescopes really replace lenses on cameras. And if you think about what a telescope is, it's really just like a fixed lens or a prime lens on a camera. So if I went out and bought a lens that only shoots 85 millimeters, not a zoom lens, but just one that shoots 85 millimeters, that would be considered prime, which means it has one focal length. And that's what these telescopes are. So whether you're using a refractor, like this one, a reflector, or a compound, Smith-Cassegrain, they all have one focal length. Now, the nice thing with these things is there's abilities to increase or decrease the focal length through some adapters. And what I mean by that is, if we move on to this picture, so over here, for example, is a barlow. So a barlow, if I compared it to a camera, would be like a tele-extender. So if I want to, take my telephoto lens and extend it by 1.5 times, then I would put that little tele extender on my camera, and it would give me a longer focal length. And that's basically what a barlow does. So if you're looking at any of the planets or that kind of stuff, well, then you might want to use a barlow because the planets are pretty small. Or if you want to get closer to the moon's craters and look at more surface detail, you might want to use a barlow. Over here is what they call a field flattener, and all that does basically is, if you're looking through, say the refractor, that the Galilean type of telescope, if you will, that one there, because of the curve of the glass, if you're trying to photograph stars, will actually show you on the edges of your picture, the stars may be all kind of like arrows. And that's just basically curvature on the glass. So what that does, that flattens out your field. So you can fix that. And on a reflector telescope, which is like those Dobsonians, they have what they call coma. It's the same kind of a thing that would straighten out and give you a nice flat image. And then the one on the bottom here is what they call a reducer. It's a focal reducer. So it does the opposite of what the achromatic barlow does here. And it actually shortens your focal length, which gives you a wider field of view. So if I had both the barlow and the reducer for my telescope, then now I have the ability to get 3 different focal lengths as opposed to just one. So there are ways, as you can see with some of these devices, that you can increase or decrease your focal length. And the only other thing, sorry, go ahead.
Well, go ahead. There was a question, but you go ahead with that when you finish that slide.
Okay. Actually, I was going to go to one more slide and then I'll answer the question if
sure.
I could.
You bet.
Okay, great, thanks. So, so the other thing adapter that you'll need if you're going to use a DSLR or a mirrorless camera now is going to be this rig right here, which what they call a T adapter. And what it is you take the lens off your camera and then you would put this T adapter in. If you get this T adapter, they are proprietary. So you have to buy a Canon T adapter if it's Canon camera, or if it's a Nikon camera, it's got to be a Nikon adapter. You'll also need a nose piece, which are universal. So typically they're a T42 thread, which is usually what's on these T adapters. What makes a T adapter proprietary to the camera is this section here that actually connects to the camera. So each camera body from the different manufacturer is going to be different. And that's why this part has to be different. But the front of it where you connect on this nose piece doesn't. So that just screws in and then you just simply slide that into your telescope. Okay, go ahead, Chris. What was the question?
So the question was from Dave McKishin. He says, Paul, where do you get your filters for the camera? Where do you get those filters for the camera?
Okay, did I talk about filters? I'm just trying to think which filters that Dave had mentioned. That's all.
Yeah, I don't think you did talk about really filters yet, but
okay,
maybe
I'll answer the question anyway.
Okay.
So Dave, to answer your question, you can get the filters at basically any telescope products vendor. Of course, you do go to Astro Buy Sell, and all the telescope vendors that are in Canada are listed right on top. You can click on any one of them, takes them right to your website, to their website. The nice thing about that is, and I do it too, and I think I recommend it for anybody, is if you're looking for any kind of a product, go to each one of the vendors and then look at the same product, because sometimes you'll find that one might be on sale, one vendor shop, but it might not be on sale on the other. Or one vendor may not even carry that, but the other one does. But in any event, it's good to get to know your vendors. And I'm not going to suggest that you go to any one particular, because virtually all of them that are on there are good vendors to go to. Or you can buy filters right directly from the manufacturers in a lot of cases. You can go right to Optilong or some of these other filter manufacturing places and order your filter. So there's a number of ways you can get them. But there's nothing here close to our area in the Maritimes, I think, that's local, unless you go to Ivan's. I'm not sure if they're doing filters, but I think if you wanted something, they could probably order you something there, and that's in Moncton.
There's always the shop of Paul Owen too. He buys and sells a lot of stuff.
Yeah.
I'm doing drums right now, guys. I'm doing drums.
So the other comment was from Dave was he was looking for filters for a DSLR camera, I guess, Paul.
Oh, okay, yeah. Okay, so again, the same sources, and you can get. There's 2 ways you can go about it, Dave. If you want to get it specifically for your DSLR as a drop-in filter, then again, there's a couple 2 or 3 of the manufacturers that actually make them for your camera specifically. So if you've got a Canon camera, make sure that when you order one, that if yours is a C format sensor, a C size sensor rather, make sure you order the one for the C size and not the full frame, because they do make for both. So just make sure that you go ahead and give them the specifications of the model number of your camera so that you get the correct one. But again, any one of those camera vendors can get you, or astronomy vendors, I'm sorry, can get you hooked in for the filters.
Perfect.
Okay. All right. So I'll go back to the slideshow and keep an eye on time for me, guys, so I don't go too long here.
Yep, we still got 20 minutes, Paul. So.
Okay, good. Okay. So what's in a camera? So when you're going to get into astrophotography, there's a lot of different ways you can go. I have a suggestion, that is, if you have a DSLR already, I would try using that first. Start off with your Milky Way shots and your you know, maybe some nice moonshots if you got a nice telephoto lens. Get a good tripod and a remote. And just start taking some pictures, getting used to the night sky to get an idea of what it's going to take to learn how to get your camera settings correct, how to get your focus set and all that sort of stuff. Once you understand your camera itself, then the next step would be to buy, if you have a telescope or if you have a friend that has one and you want to try something with a larger scale, then in the nose piece, between the two of them, it'll cost you maybe $60, so it's not a big investment. And then go ahead and try to do some stuff with that, but certainly get some guidance, watch some YouTube stuff. Our astronomy club in New Brunswick has got a lot of really good astrophotographers who are more than happy to help in any way, shape, or form to get you up and started. So, and just use your DSLR first, because if you invest in an astronomy camera, a dedicated astronomy camera, and then you decide that, well, you know what, I don't think astrophotography is for me, it's quite an investment to make in something that you may or may not want to do once you understand the processes, because it is a long learning curve that you have to go through. So if you start off with a DSLR and you get good with a DSLR, then the transition to an astronomy camera is a very simple one, and it's not really that much difference between knowing what you need to do with a DSLR than what you can do with a CCD or a dedicated astronomy camera. And at the same time, if you decide you don't want to go that way, you still have your camera for your family pictures and your fishing trips and all that kind of stuff. So I would definitely recommend that first, if I could preface all that stuff. So when we go back to what's in a camera, there are a great number of cameras on the market. There are CCD chips and there are CMOS chips, and most DSLRs use a CMOS sensor. And dedicated astronomy cameras use both CMOS and CCD. There are some differences between the two, and it used to be CCDs were quite a bit a ways ahead quite a few years ago, but the CMOS cameras are getting so good now, and the software is getting so good now that that gap has really, really narrowed a lot. So, and CMOS chips are certainly much less expensive to buy. So which is better, I guess, is the next question. So let's just do a little comparison between, say, a DSLR and an Astro camera. So with a DSLR, there are conveniences as well as just conveniences with Astro cameras. So with a DSLR, one of the main conveniences is it's multi-purpose. So you can use it in the daytime. Say if you're out at one of the star parties and you're up there for the weekend camping, you know, you take some pictures in the morning of the sun coming up, take some pictures of the birds, you know, all that kind of stuff, some family photos. And then at nighttime, you're all set and you're ready to go ahead and do some wide field stuff. So DSLR is convenient that way. It's got switchable lenses. So again, you can do, if you are using it for astrophotography at night, you can use wide angle lenses for those Milky Ways. You can use telephoto lenses for those nice moon shots and that kind of stuff. Landscape photos, sun and moon rises, all that sort of stuff. So it's very, very convenient that way. With a dedicated astronomy camera, the conveniences are, or advantages, I'll actually should say, is that if you have a camera that's cooled, in other words, keeping the camera lens cool for especially in the warmer summer nights, there's a lot less noise on your exposures that you have to deal with. Noise just being sensor noise and all kinds of stuff that happens when you're dealing with heat. So they have cooled sensors. They work great in sub-zero weather temperatures because you're really not playing with anything on them. They have very efficient sensors, which are more efficient than really what's on a lot of the cameras, DSLRs or mirrorless cameras. And you can do color spectrum separately. So with if you go to a mono camera, you can do your red colors and your blue colors and your green colors separate, or if you're going to narrow band, you know, you can do your oxygen and your hydrogen alpha and sulfur, all those things separately, because with a mono camera, which has no color on the sensor, there's no Bayer pattern on the sensor, it's quite a bit more sensitive than a color camera. So with those kind of things, that would be a convenience. If I'm doing a comparison, for advantages of one over the other, the advantages of a DSLR over an astronomy camera is a DSLR is totally self-contained. So you don't need a computer. If you have an astronomy camera, you have to have a computer. to run it, because there is no buttons on board an astronomy camera. There's no shutter speeds. There's nothing like that. Everything's done through software on a computer. DSLR will run on internal batteries for hours, whereas astronomy cameras, again, you have to use an external battery source. Some people buy marine batteries. If you're lucky enough that you have a place that you can plug in, well, you're all set that way too. Memory is stored in cards on a DSLR. I keep saying DSLR, and I'm not ignoring the mirrorless cameras. It's just what I'm used when I set this up. This is what it was. But the mirrorless cameras have these same advantages. So the memory is stored in cards on board the camera, whereas with an astronomy camera, you have to have a computer, because each time you take an image, it's got to go store into a computer somewhere to be able to access it later. But with a DSLR, you just basically, if you got a big enough chip, a big enough memory card, you're good for a couple of nights of imaging easily. And with a DSLR, with most of them today, they have the live view on the back of the camera. So you've got a built-in monitor to make sure that your pictures are coming out the way that you want. You can have a look at when you're framing things up, all of that stuff you can do with a DSLR. Again, with an astronomy camera, you have to have a computer to see anything. So in that light, in that comparison, the DSLR would have the check mark. So let me just switch to the next slide. So if you're comparing DSLRs with astronomy cameras for advantages on the astronomy camera side, well, I guess this is a couple more of the previous slide. My apologies. So on a DSLR, one of the biggest advantages of using a DSLR is a cost, because they're considerably cheaper than buying an astronomy camera. Especially one with the same size sensor in comparison, considerably cheaper. The large sensor in a DSLR is usually less expensive for the same sensor size, which I guess I just said that. And a large chip means larger field of view, and more pixels means larger printed photos. So DSLRs are really good that way. With astronomy cameras, they can be up to 50 times more sensitive than standard DSLRs or mirrorless cameras now. CCD cameras have a greater dynamic range than digital DSLRs, but although that I think is changing. So there's a couple of differences there. So the question is really, who wins? Oh. Yeah, so who wins? And that all depends really on your subject and your location. Questions, noises?
No, emails popped up.
I didn't even, oh my gosh, sorry. Okay, so the three main forms of astrophotography that are out there, really, for most of us, are nightscapes. So basically taking pictures. That's St. Rest Beach. I can't remember which moon that was, Chris, but
Well, it was a full moon.
It was a full moon. I don't know. We've done so many down there.
Was that the night we were down there doing the? We had the props with us, or?
Yes.
It was, yeah.
Yeah.
We should do that again sometime. That was a lot of fun.
Yes. It was so much fun. Oh my gosh. So there's nightscape stuff like this you can do with a camera just on a tripod, which is what this was. And then of course there's planetary, lunar, and solar. And I don't have a picture of a planet there, but I do have a picture of the moon. But it's the same sort of thing when you're taking pictures of the moon and you're taking pictures of planets. Unless you're getting into color stuff, then there's a little difference. We can get into that later. And then of course, there's also deep space objects. So nebulas, galaxies, and so on and so forth. So for planetary or lunar photography, you can use it, again, going back to the DSLR, you can use a DSLR. I use one all the time. And if it's a really, really good night, the sky, the seeing is steady, I can do one of two things. I can either go into my movie mode on my camera and then shoot a whole bunch of movies and then just process them like I would a high frame rate camera. Or I can just take, say, 15 or 20 really, really nice shots and just stack them in Photoshop and get a really, really, really nice looking image like that. So again, there's a huge advantage for a DSLR for that. For planetary cameras, of course, there's webcams you can get. This was the one that everybody started with years ago, before the they started really getting good with these planetary cameras, and that was the Philips 900C, I think, if my memory's any good.
Yep.
And absolutely wonderful webcam. You just had to just put a little nose piece on the front, stick it into your telescope, and it absolutely captured beautiful images. And now these things, people are looking for them because they were that good. You can also get cameras where you can put little fans on them and try to cool them down if you want to. But I don't know, when you're doing planetary stuff, the images, you're taking pictures so quickly that I'm not sure that that's necessary. But and then there's high frame rate cameras. You can use your cell phone now, you know. Chris, you do it all the time on the beach.
I do.
People come up, they want a picture of the moon, they want a picture of Jupiter or Saturn, pop it in there where the eyepiece goes, press the button, and there's their photo. They go home really happy. Nice, simple thing to do.
Cameras are getting awful good on cell phones now, for sure.
Oh yeah, and getting better and better and better all the time. So size really matters here, and it matters for a lot of different reasons. And I'm going to cover that in a little bit. So when you look at, when I'm talking about size, I'm talking sensor size. So when you look at that purple area, or pink, or whatever color you want to call that, that would be, say, a 35 millimeter full frame sensor. That thing is huge, right? And then you start getting into the blue ones and the yellow ones. Then we're getting into those APS-C sizes, and then 4/3 sensors, and right on down to the little tiny planetary cameras. And I'll show you what I mean by that. Let's go to an actual real picture of one. So if you look at the Sony camera, that would be a nice size sensor right there when you compare it to that little ZWO camera. See how small that sensor is versus this one? You're thinking, oh my gosh, well, I want that big sensor. Well, yes, for certain things you do. But in a lot of cases, you're going to want that little tiny sensor. And you think, well, why? Why the heck would I want to do that? Well, let me show you. So here's a picture that was taken with an APS-C. So if you have like a Canon T3i or a Nikon D3100 or something like that, they're using C-size sensors. So when I took this photograph, this was a photograph of the moon, obviously, and that little dot down there is Jupiter. So you're thinking to yourself, wow, you know, that's kind of nice. I can see that. Yeah, I can see that because I used a large sensor. And if I want to take that moon and crop in on it, I can actually see a whole lot of detail. There's a lot of pixels that are useful here. But if I look at that little spot there, by the time I got that actually cropped in big enough to see it at this size, it would just be a whole bunch of pixels, right? So this would be an improper scale between the camera, sensor, and the telescope. So when you're doing planetary, you want to use something a little bit different. You want to use, first of all, that little small sensor, because that little small sensor will be filled. It's easier to fill a smaller sensor with something this big than it is with something this big, because a lot of those small sensors, you can't even get the moon in them because it's so huge, right? So basically, this is what you end up with. So this actually is a video, but it won't play on here. But this is kind of what you would see when you're taking a picture of Jupiter. And if this was live, you'd see all the shimmering and all the air movement and all that. But this was taken with a 4,000 millimeter optical system. So basically it was an 8-inch Schmidt-Cassegrain telescope, which is typically 2,000 millimeters. 2 times Barlow puts it into 4,000 millimeters. And I used a really tiny one of those very small sensors, and see how much bigger Jupiter now looks. Jupiter now looks in this sensor like the moon looked in the last sensor, right? And this is just a little tiny chip, but that's the reason why you do that. And then when you're done processing all of that, Jupiter can turn out to look like that. So, so when you're using the right camera with the right optic system, the right focal length, you can do these wonderful things. And these things are quite easy to do. My next little slide here just shows you Saturn, which is actually smaller than Jupiter from our perspective when we look at it. And that's kind of what it would look like if you're looking at it through a live view while you're trying to image it live, just kind of a blob like this. But by the time you get done processing it, and again, the same thing as with Jupiter, a 4,000 millimeter focal length, you know, small chip. And then you can look at, again, you can actually see detail. You can see the Cassini division. You can see the color band or the cloud bands on Saturn. You can certainly see the difference between the disk and the rings. So all of those things are, if you tried to do that with a full frame camera and a short focal length telescope, you're not going to get that. You're just going to get a dot, right? So that's why when you're choosing your cameras, kind of think about what it is that you want to photograph first, and then you know basically what you're going to need. So steady seeing. So if you're looking at the moon, again, this was actually a video. It's not going to play, but unfortunately, but this was a video, and that's what the video looked like. And I think I had 600 frames, and that thing didn't move. It didn't shimmer. The seeing was so good that night. And but this is just basically a frozen, like a single frame of what was possible. If I go to this next slide, so crop sensor plus 2 times barlow in 1540 millimeters. So that probably could have been, like Mike has a 6-inch Smith Cassegrain. So if you use a 6-inch Smith Cassegrain with your DSLR, your moon would fit in very similar to this. So the moon is obviously, it's a beautiful thing to photograph, certainly. And then when you take photograph it, stack it, and all that, you can make it look like that. So, and then there's the daytime imagers. There's the sun. Well, that's a whole other kettle of fish. Briefly, with the sun, depending on your telescope, your focal length, and the kind of telescope you're using, this would have been shot with a special telescope that's hydrogen alpha, because again, when you're dealing with the sun, you always have to use the proper filtration, because it's very, very dangerous to look at the sun without the proper filters. So, but this one was done with a hydrogen alpha, so you can get all of the nice prominences, and then the filaments, and a lot of that nice surface detail. And even though the sun now is in its solar minimum, where we're not seeing hardly any sunspots, this kind of activity is always going on on the sun. So with the proper telescope, you can shoot the sun every day and see something different every day. It's fantastic. So for example, here's some prominences that are shot on the edge of the sun, and you can see some of these things. I mean, it's just unbelievable to actually watch these things. You don't see it move live because it's very slow, but you can do a time lapse on this, and then you can actually see these these prominences coming off and then going in circles, because they typically do a loop going back into the sun. A fellow named Chuck Ayoub down in Detroit does a lot of that kind of stuff. Absolutely fantastic. To get into a basic telescope with just using the Bader filter, which is it's like looks almost like tinfoil that you put over the front of your telescope, and it's what we call a white light filter. This was actually a partial solar eclipse, and the nice thing about using this was, here's the moon. This was the middle of the day, and this was shot in black and white, so the colors were actually added later. That they were false colors. But what was a bonus on this particular day, the sun had activity with spots. So not only did we get the partial solar eclipse, but we got sunspot activity at the same time. And that's just a simple Bader filter you can buy for about $60, put on the front of your telescope, and you can get this kind of imaging. Again, very, very simple things. Another white light kind of filter thing here is an actual sunspot with the umbra, the penumbra, a lot of the granulation on the sun's surface. Absolutely fantastic stuff you can do in the daytime. So astronomy doesn't have to be at nighttime. It can be in the daytime. Any questions, or am I keeping going?
Well, we got about 2 minutes, Paul. About 2.5 minutes to go. So
I'm going to stack through this really quick then. So
okay.
I'm just going to fly through this quickly. So you can do some moonrise, landscapes, and all that kind of stuff. You can get into then deep space astrophotography. That's when you get into those sensors. That's when you get into taking longer exposures and all that stuff that we talked about at the beginning of the presentation. And then when you're doing that, that's when you get rewarded with these beautiful supernova remnants, some beautiful galaxies, some incredible star clusters. And of course, the star clusters that everybody loves, the Pleiades, the Seven Sisters, M45. Yes.
These are all your photos, Paul, right?
These are all my photos. And Planetary Nebula, like the dumbbell here, I call it the apple core. And you can get in to do that. You have to have two different kind of rigs. So basically, the one on the right here with a big telescope would be an absolutely great planetary system. That's what I use mostly for moon and planets. The one on the left is a very small refractor. And those last photographs I showed you of the nebulosity, that's what I would use to get that, because I want a much wider field of view, and I'm taking a lot longer images. So the small telescope is much more forgiving on the mount with its tracking capabilities. So that's what's needed to do DSOs, deep sky objects. That would take a whole other session.
Sure would. You bet. Paul, that was
Perfect.
fantastic. Great
Okay.
presentation. Great presentation from you too, Mike. Great evening, guys. That went very well.
Okay, I'm just going to share my screen back and give it back to you.
Yep, perfect. Okay.
And there you go.
There. Okay, great. Just going to check to see if there are any more questions. Doesn't look like there are any more. So, wow, that's a wrap, guys. We're into about 30 seconds or so left. So I want to thank both of you for coming on again. Hopefully, we're going to get another clear night soon. Like I said, this is our seventh show, and we've had 2 out of 7 so far, but we've been able to fill it in with lots of topics. So if you have any other types of topics along the way, please put them in the comments after the live stream is done. I'll go back in and review them quite regularly. I see what people are posting there. So if there are other topics that you would like us to cover or discuss on another cloudy night, we're more than happy to try to put something together for you. So I guess, and also please give us a thumbs up and make sure that you've subscribed to the channel. That gives us a chance to get it out to more people as well. So from everybody here, from Paul and Mike and myself, thanks guys again. Appreciate it. And I wish everybody clear skies, and we'll talk to you all again next week. Take care, folks.
Good night, everybody.